This continues the lectures on one-dimensional motion with constant acceleration. Specifically, now we take a look at the graphs associated with three functions. We have acceleration, first of all, which is a constant. Velocity as a function of time. And then position as a function of time. When graphing out acceleration as a function of time, because the value is a constant, you end up with a horizontal line. When graphing out velocity as a function of time, notice that this function here is linear, where the slope of the line is equal to the acceleration. And then lastly, position as a function of time is a quadratic. If you recall from math class, when graphing out a quadratic, a parabola is produced. Let's immediately graph out these functions for a specific situation. Let's go ahead and copy down that example now into your notes. Let me read that example here. A car initially moving at positive 10 meters per second undergoes an acceleration of negative 2 meters per second squared for 10 seconds, and then accelerates at positive 1 meter per second squared for another 5 seconds. Graph acceleration, velocity, and position as a function of time. Label any vertices that appear on the position function. We have here two discrete time intervals with two different values of acceleration. What we have to do is calculate. Calculate position and velocity at the beginning and end of each time interval. Once we have all of that data, then we graph it out. So the first thing that we do is calculate. Let's take a look at the first 10 seconds of the problem. Okay, now by definition, let's assume that the initial position of the car, x naught, is equal to 0. And then we're given the initial velocity of the car as positive 10 meters per second, the acceleration as negative 2 meters per second squared, and the time interval itself, t, is 10 seconds long. And now using this data, what we then do is take these numbers and plug them into the expressions to calculate then position at the end of this interval and velocity at the end of this interval. Once I have that information, this then carries over into the next time interval. But for now, let's just go ahead and calculate. So what I need to do first of all is take all of this data here and then first of all plug it into the position equation to find the position x. So I have the initial position x naught, which is 0, and then v naught times t, plus 1/2 times the acceleration of negative 2, and then multiplied by 10 squared. And this ends up being 0. So notice that the object starts at the origin and ends up at the origin after 10 seconds. This then means that at some point during this time interval, the object must have turned around and moved in the opposite direction. We have to calculate when and where that occurred. Okay, next we calculate velocity. In order to do so, we plug everything into the velocity equation. So I first of all have v naught, which is 10, plus then negative 2 times 10, and this ends up being negative 10 meters per second. So the object is moving in the opposite direction after the end of this 10-second time interval with a speed of 10 meters per second. And now we then take a look to see what happens for the remaining 5 seconds of the problem. So now from 10 to 15 seconds. So the initial value of the position now, x naught, is equal to the final value from the previous interval. It's still equal to 0, but this is not by definition. It's just because the final position was equal to 0 in the previous interval. Similarly now, the initial velocity v naught for this interval is the final value from before of negative 10 meters per second. The acceleration here over this time interval is 1 meter per second squared, and the time interval itself is 5 seconds long. And then once again, what we do here is we calculate. We calculate position and velocity at the end of this interval. Okay, so just plug everything into their respective equations. Let's go ahead and calculate the position here, x first. So I have x naught, which is 0, and then v naught times t, so that's negative 50, plus 1/2 times the acceleration of 1 times the 5-second time interval squared. And this ends up being negative 37.5 meters. Negative 37.5 meters simply means that the object ends up 37.5 meters to the left-hand side of the origin at the end of the problem. And now we calculate the final velocity v by plugging in these values into the velocity equation. So I first of all have v naught, which is negative 10, and then plus 1 times 5, and this ends up being negative 5 meters per second. And now we begin to construct our graphs. When we construct our graphs, we do so in a very specific order. We graph out acceleration as a function of time, then velocity, and then position. Okay, so first of all, the acceleration is a function of time. time in seconds, acceleration in terms of meters per second squared, and then we have right here 10 seconds and 15 seconds like so. And now we have two constant values for these two discrete time intervals. So for the first 10 seconds of the problem, the acceleration is -2 meters per second squared, and for the remaining 5 seconds of the problem, the acceleration is 1 meter per second squared. Notice that we end up with this rather unusual looking piecewise function. We have a point of discontinuity here around the time of 10 seconds. How do we deal with that discontinuity? Well, let me ask you this. Is it physically possible for a car to instantaneously, literally in a non-measurable amount of time, go from a discrete value of -2 meters per second squared in acceleration to a discrete value of +1 meter per second squared in acceleration? The answer to that question is no. So then therefore what actually happens? What actually happens is the following. Over a very short time interval, the acceleration smoothly changes from -2 to +1 meter per second squared. There is some sort of complicated polynomial here that describes this non-constant acceleration. The only way to deal with such situations mathematically is by using the methods of calculus. For those of you enrolled in Honors Physics AB and AP Physics C, you will see briefly later on in this unit how we deal with such situations. But for now, when you are taught introductory physics, you are always taught the idealized versions of a situation first. The reason for that is because those idealized versions are typically easiest to deal with mathematically. Once you understand how to deal with those situations, then we begin to add layers of complexity, eventually approaching physical reality itself. But for now, we just ignore this smooth curve polynomial and we end up with the piecewise discontinuous function that we had earlier. Let me just go ahead and resketch it. Okay, so once again, acceleration is a function of time, 10 and 15 seconds. We have our values of -2 meters per second squared, and then right here, +1 meter per second squared, and then we just leave it at that. Okay, next we graph out velocity as a function of time. Okay, velocity in terms of meters per second, here's 10 and 15 seconds like so. Let's take a look at our data up here on the top board. At the beginning of the problem, the velocity is at 10 meters per second. And at the end of 10 seconds, the velocity is at -10 meters per second, like so. And then what connects these 2 points is a line. The slope of that line is the acceleration of -2 meters per second squared. That then looks like this. Let me use a different color here once again. There we go. Like so. The slope of this line is the acceleration of -2 meters per second squared. And then notice what happens right here at this instant in time. At this instant in time, the velocity is 0. This is the turnaround point. This is when the car is going from a positive value of velocity to a negative value of velocity. We have to figure out when this happens. Now, if you look at the symmetry of this graph, pretty obviously this moment in time right here is 5 seconds. But here's then actually how you calculate it. What we do is we take the velocity equation and we set the velocity v equal to 0 because that's what the value is at this instant in time. And then algebraically, we then just solve for the time t. So move the v0 to the other side, we pick up a negative sign when we do, and then divide by the acceleration a. That then gives you the following. Plug in the numbers. Negative and then 10 meters per second divided by -2 meters per second squared gives us a time here of 5 seconds. That's this point right here. And then lastly, for the remaining 5 seconds of the problem on this graph, we then go from a value of -10 meters per second to -5 meters per second. So let's say, for example, that right here is -5 meters per second. So then therefore at 15 seconds, we have this point. Once again, connecting these 2 points right here is a line. The slope of this line is the acceleration of 1 meter per second squared. That looks like this. Once again, we have a point of discontinuity here. This discontinuity corresponds to what's happening right here at this instant in time of 10 seconds. We ignore that mathematical detail. Okay, and then lastly, we graph out the position as a function of time. Okay, so 10 and 15 seconds, like so. And now we once again take a look at our data. Look at the initial value of position and the final value of position. Notice that they are both 0, here and here. And then now what's connecting these 2 points is a parabola. The reason for that is because the position as a function of time is a quadratic function. The acceleration being negative over this time interval indicates that the quadratic term is negative. This then means that the parabola opens downwards. The parabola looks like this. Notice that there is a vertex right here for this parabola. This occurs at 5 seconds. At that instant, the velocity is 0. How do we know this? Well, recall the following. The derivative of position with respect to time is velocity. Recall that the derivative is the slope of the line that is tangent to the curve. So now I'm going to use the ruler's edge here to represent the tangent line. Let's say that we're talking about this time here at times t is equal to 0. Notice that the slope of the line there is a positive value. The positive value is the velocity right here of 10 meters per second. And then the velocity goes from 10 meters per second to a velocity of 0 right here at this instant when the time is 5 seconds. That's this point right here. And then lastly, we then go from a velocity of 0 to a velocity of negative 10 meters per second right here at this point. Once again, the derivative of position with respect to time is velocity. And now I have to figure out where this vertex is. I have to find this position here. In order to do so, we plug into the position equation the following data. We have x naught, which is equal to 0. The initial velocity v naught of 10 meters per second. The acceleration of negative 2 meters per second squared. And now we set the time t equal to 5 seconds. We then take these values and then plug them into the equation for the position x. Let me go ahead and do so. So x naught is 0, and then v naught times t plus 1/2 times the acceleration times the time squared, and I end up here with a position x of positive 25 meters. That's this point right here. And then lastly, the remaining 5 seconds of the problem, we go from a position here of 0 to a position of negative 37.5 meters. Let's say that that happens to be down here somewhere, like so. Like so. And then connecting these 2 points is another parabola. In this case, however, the parabola opens upwards. The reason why the parabola opens upwards is because the quadratic term, the acceleration is a positive value. This then means that the parabola opens upwards for that reason. We do not, however, encounter another vertex in this parabola, and the reason for that is because over this time interval, the velocity does not become 0 again. So then therefore you end up with a piece of a parabola, if you will, that looks something like this. Like so. And then once again, here's how you can understand why that parabola looks the way it does in the context of the derivative, the slope of the tangent line. So on a position as a function of time graph, the slope of the tangent line is the velocity. So right here at 10 seconds, the velocity right there is equal to negative 10 meters per second. That's at this point right here. And then the velocity goes from negative 10 meters per second to negative 5 meters per second, like so, right here at this instant in time of 15 seconds. And then the last thing for me to do with regards to this problem is actually mimic the motion. Let me go ahead and walk the problem. In order to do so, however, bear with me for a moment. I'm going to have to move my phone. I'm going to have to move my camera. All right, so let me do so by doing the following. Like so. And then when it comes to mimicking this motion, the easiest thing to do is to look at the parabolas associated with the position as a function of time. And here's then how I'm going to set this up. I'm going to say at the edge of the desk here is the origin, and then therefore when I walk past the edge of the desk, this then means that the problem starts. When I walk past the edge of the desk, however, I'm moving to the right-hand side of 10 meters per second. And then what I do is slow down and stop for an instant, turn around and move in the opposite direction, and then slow down as I eventually pass the desk's edge, moving then to the left-hand side. So then therefore, the motion looks something like this. Start, parabola, vertex, turn around, past the origin, slow down as I do, and then the problem ends. So all of that is necessary to describe somebody just walking back and forth in front of the desk. I said at the outset of kinematics that ultimately describing, mathematically that is, describing motion is difficult to do. This concludes the lectures on one-dimensional motion with constant acceleration.